Yes. All right. So last week we started from talking about the historical introduction to blockchain and cryptocurrencies. So let me recap what we have talked about. So this will be our course content. So this week's topic will be cryptographic hash functions for blockchains. So in the following weeks, we will talk about digital signatures, elliptic curve cryptography for blockchains. Then we will talk about multi-signatures, and then we can move on to cryptocurrencies and talk about mining and consensus models, soft forks and hard forks, smart contracts, NFTs, and so on. So let me remind you what we have talked about so far. So we said that we don't like the word of using the word crypto is used in a wrong way. Cryptographers are a little bit angry about this. So crypto actually means cryptography, not cryptocurrency. So we mentioned that the internet and the public key cryptography made it possible to, talk about electronic money, and some people desire to have more anonymity using cryptography and have, payment systems so that we don't have to give too much information to the banks or the governments and so on. So cypherpunk community really wanted something to have digital money so that there is no central authority, and it is designed in a very good way so that it will prevent double spending and it will provide anonymity. So Bitcoin actually solves this problem, but solves the anonymity problem in a halfway, let's say. So there's pseudo-anonymity in Bitcoin, but now at the end I will talk about zero-knowledge protocols and talk about how we can obtain full anonymity in a cryptocurrency. So the important thing is that almost every e-cash company failed until the invention of Bitcoin. So this is why it is a huge progress. So it was introduced in 2008. It is decentralized, so it keeps every transaction, every operation on the network on a ledger, which is distributed among people, which is publicly available. You can just install the software and download the whole blockchain, which is around 390 gigabytes. Since all of the transactions and all of the accounts are public, it doesn't provide anonymity, but we don't know which account belongs to whom. So this way it provides pseudo-anonymity. So we mentioned that Bitcoin has no encryption. Integrity of ledgers are provided by cryptographic hash functions. Double spending is prevented by proof of work, which is again provided by cryptographic hash functions. So we have hash puzzles here. But in order to send Bitcoins, a transaction is authorized. So we need digital signatures. And this is where cryptography comes into play. So we have cryptographic hash functions and digital signatures. So I told you before, Bitcoin has pseudo-anonymity. Account numbers are cryptographically obtained values and do not contain personal information. So here's a sample picture of what a blockchain looks like. So you have the block data here and the header here. So block data consists of all of the transactions. But if you hash all of them in pairs, you obtain a Merkle root at the top, and you put it in the header. And all of the blocks are connected to each other by using the previous hash of the block. So this way you kind of add blocks to each other. This is why we call it a blockchain. Okay. And this nonce value comes from mining. So we talk about the Genesis block. We said that it was really mined at the starting date of this blockchain, 3rd of January. And we mentioned the specifics of Bitcoin. So the block size is 1 megabytes. A block addition time is 10 minutes. Total Bitcoin amount can be at most 21 million. And the award of miners are halved in 4 years. So if you make any change to these specifications, this causes a hard fork. But if you make a small modification, for instance, if you add a new algorithm or add a new property, that would allow soft fork. By hard fork, we mean that you make a change that is not backward compatible. Okay, so this means that once you make a hard fork, you actually create a new blockchain. But if you create a soft fork, like adding a new cryptographic algorithm, the people who updated their software will still be able to communicate with the people who didn't update the software. Okay, so it provides a backward compatibility. So people with the new software will still understand the transactions provided by the old miners, let's say. So we said that Bitcoin and similar cryptocurrencies use proof of work. So you prove that you really spending your CPU cycles to show that you really do the work. But nowadays you cannot do this by using CPUs or GPUs or FPGAs. Bitcoin can be mined only by ASICs, but different cryptocurrencies make it hard to provide an ASIC for that mining algorithm. So you can use GPUs to, for instance, mine Ethereum, but not Bitcoin. So this is one of the concerns about the cryptocurrencies. The electricity consumption is huge. Currently, it is not that big, but it's increasing. And during the pandemic, it really increased a lot. I think before the start of the pandemic, Bitcoin mining's yearly electricity consumption was around 70 to 80 terawatts. But now it is 200. It's almost 3 times larger. So we don't know what will happen in the following years. So there's a huge concern. So for this reason, some people try to change proof of work algorithm to different consensus models. For instance, Ethereum, since the beginning, tries to move on to proof of stake instead of proof of work, but they still couldn't do it. And we don't know in how many years they can achieve this. So here's an example for a Bitcoin block. This is the result of the hashing puzzle. So there are too many zeros at the beginning. You can see that. And if the difficulty increases, as written here, you have to come up with more zeros here. So this is how the hardness of the hashing puzzle is determined. So we talk about a little bit about NFTs. So there's a lot of misconceptions about NFTs. Maybe we should briefly mention some of them. And an NFT actually is not a copyright, okay? When you buy an NFT, you don't buy the copyright. You just merely saying that you are the owner of that digital data, that's it. That is not the same thing as copyright, okay? And one of the problems is that people think that whenever you create an NFT, people think that it is stored in the blockchain. But almost none of the NFTs are stored in the blockchain, okay? Because most of the time you're actually putting an image or a video file that can be most of the time up to 50 megabytes, and you cannot store all of this data on the blockchain. Very rarely you can see some projects where people really put the NFT on the Ethereum blockchain, but in those scenarios you are allowed to, like have FE pixels, so you can modify them. So this is why you cannot have something with a big resolution in the blockchain, okay? So if it is not stored in the blockchain, then where it is stored, that is a huge problem. Actually, this storage problem is valid for almost everything, even for your own data. You have to decide where you should store it and where you have a backup and so on, right? So a similar thing happens in the NFTs. So one way to put the NFT in a web page, like using a HTTP or HTTPS, and some $1 million NFTs are stored in this way. But the problem is that you cannot be sure that that web page will provide the same image in the future, right? Moxie made a fantastic example. So he created an NFT and put it in his web page. But since it is a web page, it runs on an Apache server. And depending on the requester, the server can show you a different image, right? This is how a web page works. So if you look at Moxie's NFT at OpenSea, this is the image you will see. And at Rarible, it will look like this. But if you own the NFT, you will use a wallet to look at them. And if you look at this NFT at MetaMask, it will appear like this. Okay. So the storage is a huge problem. So keeping it in a web page is not a good idea, because maybe in the future you will not pay a domain name money for that web page, and somebody else will buy the domain and put a different image there. So storing NFTs in a web page is not a good idea. Currently, a lot of marketplaces use IPFS. It is like a torrent. So your image is actually divided into pieces, and different people in the network stores them. But this is also another problem because you don't know if everybody will, keep that image in their servers, let's say, because as you can see, even what happens in the torrent is that sometimes some of the files you downloaded years ago are not available today, right? Actually, this happened in NFTs. Some NFTs became unavailable even if they were uploaded to IPFS. So once we informed the marketplaces, they re-uploaded them, so they became available, but it shows the problem that some NFTs in the future will be lost. Okay, so we will talk about them in detail in the future. Okay, so I already mentioned that the cryptocurrency name suggests that there is an encryption involved because people think that cryptography is equivalent to encryption. But cryptography is used for many different scenarios. And in cryptocurrencies, we use cryptographic hash functions and digital signatures a lot. And this is why we will be focusing on these topics. But I also mentioned that also Bitcoin uses hash functions and digital signatures. Other areas of cryptography came into play when we developed new cryptocurrencies or new blockchains. So zero knowledge protocols are used in some cryptocurrencies to provide full anonymity. And post-quantum crypto actually affects us because all of the digital signatures we use today in blockchains will be broken if a huge quantum computer is built. Okay. And lightweight crypto is somewhat important in blockchains where you use IoT devices because you would need performance there. Okay, so we said that hash functions are used for many properties for a blockchain, like address derivation, securing the block header, securing block data, creating unique identifiers, or creating cryptographic puzzles. And we said that Bitcoin supports 3 hash functions, but SHA-1 is almost never used because it is already broken, because it doesn't provide collision resistance. We found collisions for SHA-1. And in order for a digital signature to be secure, the underlying hash function should be collision resistant. So this is why we don't use SHA-1 also for digital signatures. Okay, but RIPE-MD and SHA-256 are extensively used in Bitcoin. So there are opcodes for them. And Ethereum is developed years later, so it uses SHA-3. It is the Ketchak algorithm which won the SHA-3 competition. But I also mentioned that there are many mining algorithms that use many different hash functions from the SHA-3 competition to make development and ASIC hard. So for some of these algorithms, actually people build ASICs. But if you make their work even more complicated and harder, for instance, if you introduce randomization and so on, it will be harder to build ASICs for this kind of mining algorithms. Okay, we briefly mentioned what the discrete logarithm problem is, and we said that elliptic curve cryptography will be used because Bitcoin and almost every other cryptocurrency use the same elliptic curve that is chosen by the Bitcoin. And instead of working on numbers from number groups, we actually work on points on elliptic curves when we are signing a transaction. So we will talk about elliptic curve cryptography, and we will talk about how the addition operation is described in this kind of elliptic curves. Okay, but I mentioned that it is possible that a huge quantum computer might be built in the future. So we are not expecting actually this to happen in a few years. I mean, people most of the time send tweets expecting to have such a computer in 2024. But looking at the technological advancement, we are not expecting such a computer in the recent years. But if it is built in maybe 30 years later, it will be a problem. So because such a quantum computer can break the discrete logarithm problem, or can solve the integer factorization problem, or elliptic curve discrete logarithm problem in polynomial time. So we have to update these signature algorithms in the future to be quantum resistant. Okay. So So far, this is what we have talked about. What we didn't have the time to talk about zero knowledge proofs. Cryptocurrencies like Bitcoin provide pseudo-anonymity. We mentioned this because we know which account has how many Bitcoins and which transaction is performed from which account to which. So everything is transparent, but we don't know which account belongs to whom, right? So if you send a tweet saying that this is my account, then we can, connect this Bitcoin account to your real world identity. But if you don't do it, it will be hard to guess who is who. But this provides pseudo-anonymity, and at some point, if you try to, withdraw your money, then you have to provide your real identity, and your anonymity will be broken. So to obtain anonymity, users use some non-cryptographic techniques like mixing. So in the mixing, if you want to send one Bitcoin to one person, you also invite 10 different people, let's say, and all of you send one Bitcoin to somebody else. But those 10 people will send those Bitcoins to themselves in a different account, but only you will send it to another person. This way, when somebody looks at the transaction, they will see that 11 people sending money to 11 people, so they will have to work more to find who is sending the money to whom. Okay, but these are non-cryptographic techniques, and you have to trust everybody involved in this mixing operation and so on. So in order to avoid this, two protocols are announced: Zero Coin and Zero Cash. They provide anonymity at the protocol level by using zero knowledge protocols. So main idea behind zero knowledge protocols is that one party can prove that they know a value X without revealing it. So this is the main idea behind zero knowledge proofs or protocols. So Zero Coin has the following idea. This protocol uses two coins, let's say A and B. To obtain anonymity, a user obtains anonymity by destroying A coins and minting same amount of B coins. So let me explain this in a better way. Actually, this protocol first proposed for Bitcoin. So if you want to make a change in the Bitcoin, you can send a proposal. They are shortened as BIPs. And if everybody agrees that this is a good improvement, they would use it in the Bitcoin. So this was initially submitted to be a property of Bitcoin, but if you make such a change, it will create a hard fork, and generally Bitcoin developers try to avoid creating hard forks. So this is why they rejected this or haven't accepted it yet. But for this reason, the designers of this protocol created their own cryptocurrency and use it there. So idea is as follows. Assume that we provided this property for Bitcoin. So it will happen like this. For instance, you have Bitcoins, like the current blockchain. So instead of sending your Bitcoin, for instance, I want to send 2 Bitcoins to some person. Instead of sending it directly to a Bitcoin account, we create a different coins, let's say B coin. Okay, so I destroy my 2 Bitcoins, and by destroying it, I generate 2 new B coins. Okay, so I send these 2 Bitcoins to your B coin account, you receive it, then you destroy it there and generate 2 Bitcoins in the original blockchain. So this way you are actually hiding who is sending money to whom. But in this protocol, the transactions amounts are not secret. So just by looking at the transaction amounts, you can guess who is destroying and who is sending to whom. Okay, but it still provides good solution. So something better followed it. It is called Zero Cash. This time they use zero knowledge snarks. So there is a good abbreviation for this, which make zero knowledge proofs much more compact and efficient to verify. So this way, instead of the zero coin, you can do the same thing using a single blockchain. Instead of 2 cryptocurrencies, you can do it with a single one if you use Zero Cash. And the zero knowledge proofs you provide are small, like less than 300 bytes. So when you look at this kind of protocol, what you see is that money is moving from a group of people to a group of people, but you don't see actually which person is sending to which. So in theory, this is how it works. But in order to create such a protocol, you have to initialize it by first choosing 2 random numbers and multiplying them and keeping them secret, because if somebody knows them, they can break the system. So it requires a initial starting point, let's say. And since we rely now on the multiplication of two primes, if you solve the integer factorization problem in a fast way, this means that you can break this protocol. So this is why it is not post-quantum secure, okay? Because I already mentioned that quantum computers can factorize numbers in a very fast way. There are different alternatives for this. Currently, there is something called Starks. They are also zero-knowledge proofs, and they are quantum secure, but proof sizes are larger. Like, you know, at this time it is at the level of kilobytes. So you can provide anonymity using this kind of protocols, but it will be it will take large amount of data. I mean, the storage will be harder because you need to store more data on the blockchain. Okay. So now maybe most important part that we have to talk at the end of this course, but now we have to initially agree on it. So blockchain was a huge hype, right? In the probably last 10 years, everybody's talking about Bitcoin and blockchain, and people make remarks saying that it is the biggest invention since the internet, right? You might hear a lot of nice things about blockchain, but the question is that if it is something that good, why don't we use it in different scenarios than cryptocurrencies, like, right? Because we hear blockchain all the time, and if somebody asks you where do you use it, actually you don't hear a nice answer, because most of the time there isn't a good reason for you to use a blockchain. So in the last years, a lot of people started to write papers about why you do not need a blockchain. Okay, so in order for you to use a blockchain, you really need a use case for it. In the cryptocurrencies, blockchain solves this problem in a very nice way. So we have a solution called blockchain. Now we have to come up with questions that this solution is applicable, right? So people come up with a lot of different ideas. They say that, okay, we can use blockchain here and here. So you can search the internet and find thousands of papers using blockchains in different scenarios, but most of the time, actually, they are not necessary, and unfortunately, most of them are wrong, okay? So a blockchain might be useful if a shared and consistent data store is needed, okay? So this is what actually fails most of the time. A lot of companies ask me to consult them. They say that they want to use a blockchain. And I ask them if they need a shared and consistent data store, and they say they know. We store everything in our database. Then I say then you don't need a blockchain, okay? And they say that, okay, we heard that it is something new, so this is why we want to use it. We don't know what it is. Okay, so this is the first. If you say no to this question, then you don't need a blockchain. If you say yes, then you have to answer the following question. So you can see flowcharts for this kind of stuff, okay? So a blockchain might be useful if data is contributed more than one entity or auditing is required. So this is important. Most of the blockchain solutions you hear on the internet or in the papers, actually only one entity is contributing data and they don't need auditing. So actually in that scenario, you don't need to use a blockchain. You can just go and use a database, okay? Third, records are never updated or deleted after they are written. This is a property of blockchain, so you need to have a case where records are never updated. Sensitive data will not be stored as plain text. Some people wanted to, put their company secrets on the blockchain as a plain text, which is not meaningful. Control of the data store cannot be assigned to a single entity. This is why we're actually having a distributed system. So if you can leave the storage of the control of the data to a single entity, if you trust them, then there's no point of having a blockchain in the first place. And it might be useful if tamper-proof log of all data store rights is wanted. Okay, so if you say yes to all of these questions in a use case, then maybe blockchain might be useful for you. Okay, so you have to keep this in mind all the time. So people always come to me with an idea saying that, okay, we can use blockchain here, And I asked these questions to them, and they realized that they actually don't need a blockchain there. Okay, a traditional solution like using a database or an encrypted database would solve most of your problems. So if you use blockchain instead of a database in the scenario, everything will be much slower, and everything will be, you have to need more storage to make everything more meaningful at that point. So most of the time, unfortunately, you don't need a blockchain. Okay, so this is maybe the main takeaway from this course.